Hello students, welcome back. Previously we completed up to section 2. Now let's go to section 3, primitive roots of primes. Before starting the main topic of section 3, however, we have to start with a bit of a preparation. So we begin with a digression rather. But do not take it lightly because this is important in terms of both its standalone quality and also the implication to lesson 12. Let's study some polynomial congruence modulo prime. Let P be a prime and let F be an integer coefficient polynomial with degree n, like this. Sorry, I babbled a little bit. Then, here's the conclusion. The polynomial congruence, f of x is congruent to 0 modulo p, has at most n incongruent solutions. Before proving it, I'd like to make a couple of remarks. Number one, the condition modulo prime is important here. The conclusion does not work if we drop that condition. Here's a counterexample. There are many more, but here's one. X squared minus 4x plus 3 is congruent to 0 mod 8 is a quadratic polynomial congruence. Degree is 2. But do we have at most 2 incongruent solutions? No, we have 4. So why does it fail if we drop mod p condition? And why does it work for prime? Well, the key point is division. That's my second remark. Modulo prime, the division is well defined for all non-zero elements, same as in Q, R, and C. Not coincidentally, therefore, we have these kind of corresponding results for Q, R, and C. So if f of x is a polynomial with rational coefficient, then it has at most n rational zeros, and same for real, and same for complex as well. In a special case for complex polynomials, as a matter of fact, we can say that f of x has precisely n complex zeros if we count in all the multiplicities. But if we discard all those overlaps, the duplicates to multiplicities, then yeah, we have the same thing, at most n complex zeros. Same as here, at most n incongruent solutions, modulo p. Alright, done with the remarks. Let's go ahead to the proofs. We're going to use the induction on n. The base case is something we already did in lesson 6. That's linear congruence. If A is non-zero, in other words, well, A is non-zero mod P prime, that means A and P are relatively prime. So AX is congruent to something, we can divide by A. The multiplicative inverse A inverse exists if and only if A and the modulus are relatively prime. Remember that? And if it exists, then the existence is unique, those sort of thing. And you have to go all the way back down to the linear Diophantine equations and whatnot. But we went through all those before. And modulo prime, of course, it works out generally okay for whatever non-zero element. So we can do the division and we get the unique solution. So that's the base case. Next, the inductive hypothesis. Assume the conclusion is true for the degree n minus 1, and then let's go ahead to prove it for the general case with degree n. Suppose that x is congruent to alpha is a solution. In other words, f of alpha is congruent to 0, put alpha there, modulo p. Wait a minute, can we always do that? What if there is no solution? Well, in that case, there's nothing to prove. I mean, we don't even have to mention it because no solution means 0 solution. Certainly 0 is less than n, the problem says at most n, so less than n is okay. So it doesn't even, it's not even necessary to mention it. So let's begin with x is congruent to alpha. And then let's go ahead with the division algorithm. Divide f of x by x minus alpha. And you're going to get this. Q for quotient and r for remainder. And please note that r is a constant. Previously, we can have r of x, but x minus alpha has degree 1. So the remainder has to have degree less than 1. So degree 0. So it's a constant. Now, put alpha in place of x. Then f of alpha is 0 because alpha is a solution. So f of alpha is 0. And putting alpha right here, alpha minus alpha is 0. So 0 times q of alpha, this entire thing is 0. The conclusion, 0 plus r is 0. So r is congruent to 0 modulo p. So r is 0, so we can drop it. As a result, we get f of x is congruent to x minus alpha times q of x. No divisor, no remainder. And the degree of q is n minus 1. X minus alpha has degree 1 and n has degree n, so q must have degree n minus 1. Degree n minus 1, alright, we can apply the inductive hypothesis. The polynomial q of x has at most n incongruent solutions, namely alpha 1, alpha 2, alpha 3 up to alpha n minus 1, which do not have to be distinct. If they're all distinct, then we have precisely n minus 1 incongruent solutions. But if there's some overlap, if there's some redundancy, then less than n minus 1, then that's okay, because the problem said at most n minus 1 incongruent solutions. Now, we got up to here, at most n minus 1 incongruent solution for q. Now for f, well, we know alpha 1, alpha 2 up to alpha n minus 1 are solution for f as well, because q of those alpha I is 0. So 0 times something is 0, so yeah. What if there is yet another solution, completely different solution, beta, distinct from any of those alpha 1 through alpha n minus 1? Then, by the inductive hypothesis, q of beta has to be non-zero. Please make that observation. Why? Inductive hypothesis says q of x is congruent to 0 has at most n minus 1 incongruent solutions, and they're listed alpha 1 through alpha n minus 1. Beta is different from all those, so q of beta should not be 0. So that's non-zero, so we can divide it away. If we do that, you're going to get beta minus alpha is congruent to 0. You see, multiply this multiplicative inverse of q of beta to 0, then you're going to get 0. So beta minus alpha is 0. Consequently, alpha is congruent to beta modulo p. So what conclusion do you get? If beta is different from any of those alpha 1 through alpha n minus 1, then it has to be same as alpha. Therefore, there are total n minus 1 plus 1 n possible solutions. So we have n incongruent solutions. That completes the proof. Okay, we went through the polynomial congruence. Let's talk about how to use it for lesson 12. Let's apply that to roots of unity modulo prime. If p is prime and d divides p minus 1, then x to the d power is congruent to 1 mod p has exactly d incongruent solutions. Well, from Lagrange's theorem, at most d incongruent solutions, we can get that. But it could be less than d, maybe all the way to 0. But this theorem says, this corollary says, exactly D incongruent solutions. How can you say that? Well, let's begin with Fermat polynomial, x to the p minus 1 power minus 1. And this thing is congruent to 0 for all non-zero x value. So x is 1, 2, 3, 4 up to p minus 1, then fine. X is 0, then of course that's different, but we are not considering 0. And then from here, let's apply this cyclotomic factorization. We can rewrite it as x to the d to the q power, because d divides p minus 1, q for quotient, d minus q is p minus 1, yeah. And then we have something to the q power minus 1, so x to the d power minus 1, and then the cyclotomic polynomial here. Q minus 1 power, Q minus 2 power, Q minus 3 power, all the way up to 0 power added. This kind of polynomial is called cyclotomic. So cyclotomic polynomial of x to the d power. So let's name that as f of x. And this Fermat polynomial, x to the p minus 1 power minus 1 is x to the d power minus 1 times f of x. That's what you get so far. And then we're going to use these. Fermat's theorem, x to the p power minus 1, x to the p minus 1 power minus 1, excuse me, congruent to 0, has exactly p minus 1 incongruent solutions thanks to Fermat's theorem. X can be 1, 2, 3, 4 up to p minus 1. Anything other than 0 will do. And then Lagrange's theorem, f of x is congruent to 0, this one here, will have d times q minus 1 incongruent zeros, because that's the degree. And finally, Euclid's lemma gives us there's no zero divisor modulo p, or as a matter of fact, you can divide by any non-zero element. So if this is 0, the left-hand side is 0, then either this is 0 or that's 0. That conclusion, that's coming from Euclid's lemma. In short, we claim this, at least D incongruent solutions, thanks to this. P minus 1 solution, precisely P minus 1 solution from here, left hand side. And then at most, D times Q minus 1 solution from f of x. So otherwise, this has to be 0. So subtracting one from the other, we get D. So precisely this minus at most this. So we get at least D incongruent solutions. So this thing has at least D incongruent solutions. However, Lagrange's theorem says at most D as well. So combining those, at least D from this computation and at most D from Lagrange's theorem, we get precisely D incongruent solutions. By the way, let me open up this computation again. Precisely P minus 1 solutions from here. And then at most D times P minus 1 solutions from here. So otherwise, solution must be coming from 0 here. So subtracting one from the other, we get D. But precisely P minus 1 minus at most D times Q minus 1, so at least D. And also at most D. Conclusion, precisely D solutions. And that's what we wanted all along.